Hi, Ali. You look a little confused. What's up?
This part of the lecture notes, it's about finding the basis and dimension of a subspace. I don't get it. It seems really complicated.
Ah, I see. Let's go through it together. It's not as bad as it looks, I promise. See the first page? It's introducing the problem.
Yeah. How can we find a basis and the dimension of W? And W is some subspace generated by a set of vectors. I know what a subspace is, but I always forget the difference between a basis and a dimension.
I know what you mean. It can be tricky. Let's just start with the basics, since the notes do a quick review.
Okay. A basis of a subspace W is a set of vectors that are linearly independent and generate W. And the dimension of a subspace W is the number of basis vectors.
Exactly. So a basis is a minimal set of vectors that you can use to create any other vector in the subspace. And the dimension is just how many vectors are in that set. It's like the rank of the space.
Okay, that makes sense. But then it talks about elementary row operations and elementary matrices.
Right. This is the key to the whole process. These are the operations we use to simplify a matrix. You know them, right? Swapping rows, multiplying a row by a scalar, and adding a multiple of one row to another. The notes say an elementary matrix is just a matrix that does one of these things. The important thing to remember is that these matrices are invertible.
Okay, invertible. And that leads to the reduced row echelon form, RREF. It always looks like a bunch of ones, zeros, and then some other numbers.
That's the basic idea. The key takeaway here is what a pivot column is. It's any column that contains a 1, which is the only non-zero entry in its row. That's the part that really matters for what we're trying to do.
So for any matrix A, there's some invertible matrix P that turns it into RREF, and the rank of the matrix is the number of pivot columns. I remember that part.
Perfect. You've got the building blocks down. The next few pages are just the proofs for why this method works. See this first lemma? It says that a linear combination of vectors is 0 if and only if the linear combination of those same vectors, but multiplied by an invertible matrix P, is also 0.
Wait. So A1 V1 plus equals 0 if and only if A1 PV1 plus equals 0. Why is that important?
The proof on the next page shows why. It's because P is invertible. We can multiply by P to go one way and multiply by P inverse to go the other way.
Oh, I see. It's an if and only if statement. So P doesn't change the linear independence of the vectors.
You got it. And that's exactly what the next lemma says, which is really just a restatement of the first one. A set of vectors is linearly independent if and only if the set of those vectors multiplied by P is also linearly independent. The proof is on this page. It's simple, right? If we assume V1 through VR are linearly independent, and we have a linear combination of the PVIs that equals 0, then by lemma 1, the linear combination of the original VIs must also be 0. Since we started by assuming they're linearly independent, all the coefficients must be 0. The other way is the same logic, just with P inverse.
Ah, so if we apply elementary row operations to a matrix, it doesn't change whether its original columns are linearly independent or not. That's a huge insight.
Exactly, and that's why this method works. These notes summarize the steps nicely.
Okay, let's go over them again. Form a matrix A with the vectors as columns. Find the RREF of A. Identify the pivot columns of the RREF. The original vectors corresponding to the pivot columns are a basis for W. The number of pivot columns is the dimension of W and the rank of A.
You've got it. The theorem on the next page states this process more formally. Have a look for a second. Now let's see it in action with an example.
Okay, 5 vectors in R4. We need to find the basis for the subspace W that they generate.
The first step is to form the matrix A with these vectors as its columns.
And the second step is to find the RREF. I'm not going to do all those raw operations right now, but the notes say the RREF is this matrix here. Let's call it PA.
Good. Now, the next page shows the pivot columns.
The pivot columns are the first, second, and fourth columns.
Right. The ones with a single one in them. So, according to our steps, what's our basis?
The basis is the original vectors corresponding to those pivot columns. So it's v1, v2, and v4.
You got it. And what about the dimension of W?
The dimension is the number of basis vectors, which is the number of pivot columns. So the dimension of W is 3, and the rank of A is also 3.
Perfect. The next page is a remark that really helps with the intuition.
Oh, right. The non-pivot columns are just linear combinations of the pivot columns. So PV3 equals negative PV1, and PV5 equals PV1 plus 2 PV2 plus 3 PV4. And since P is invertible, we can say the same for the original vectors. V3 equals negative V1, and V5 equals V1 plus 2V2 plus 3V4. That's why we don't need them in the basis.
Exactly. They're redundant. We don't need them to generate the space. The basis is the smallest set that can do it.
The notes have a nice summary here. The rank, the number of pivot columns, and the dimension of the column space are all the same value.
And this final page puts it all in a nice little summary. Form a matrix, find RREF, identify pivots, original vectors are the basis, number of pivots is the dimension and the rank. You've got this now, right? It's just a process.
Yeah, I think I do. Thank, Hana. It makes so much more sense when you talk it out. I just kept getting stuck on the lemmas.
No problem. That's what friends are for. We can go over the next set of notes when you're ready. Maybe we can grab a coffee first.
Sounds great. Thanks again.